In this video, we'll talk about the second option for eigenvalues or for roots of a polynomial in general, and those are complex eigenvalues. So there are just a lot of matrices where the eigenvalues are complex. There's not much that really can be done about it. That's just how these things happen. However, we know that in that case, the corresponding eigenvector will also be complex because we're starting with a real matrix. We have the normal equation for eigenvectors, that is that A times the vector v equals lambda times the vector v for vector v and eigenvalue lambda. Now, if A is a real matrix, that is, it has all real entries, and lambda is a complex number with non-zero imaginary part, then V must also be complex in some sense. Otherwise, there's no way this can work out, right? If V is a real vector, the left side's entirely real, the right side is not. So V is going to have to be complex to sort this out. But that, sort of no pun intended, complicates our process a bit, because we got V by solving a homogeneous system that we could get from real numbers just the way it was. In this case, we're going to have to figure out V as a solution to equations again, but we're going to have complex coefficients in that equation. And this will get pointed out in the example later, but the hardest part here is seeing the redundancy of the equations, because in the real case, it was pretty obvious when I had one equation that was a multiple of the other. That was pretty clear because it was just double every entry. Great. When you do it with complex numbers, you're going to have equations that are complex multiples of each other, and it's going to be harder to see the redundancy and make things cancel out in a nice way to have it work. In these sorts of situations, your best friend is multiplying by the complex conjugate to get the first column of the matrix all into real numbers and then comparing the equations from there. So use complex conjugates to see how it works. But thankfully, with complex numbers and the structure that they have, we get a nice little benefit from this trying to find eigenvalues and eigenvectors. That's why we really only have to find half of them. The result in this front is that if I have a real matrix and a complex eigenvalue with eigenvector v, then lambda bar, the conjugate number, is also an eigenvalue, and the eigenvector is also the conjugate. And this one just comes back to our equation again. If I have that a v equals lambda v, and A is a real matrix, I can conjugate both sides of this equation. Since A is real, it's not affected by the conjugate at all. So this just becomes A times V bar equals lambda V, and by property of conjugation, this is lambda bar V bar. So if lambda was an eigenvalue with eigenvector V, then lambda bar is also an eigenvalue with eigenvector V bar. This means for each conjugate pair of eigenvalues, I'll have to find one eigenvector, and I know the other one for free. This is similar to the idea of knowing that if I find a complex root for second order equation, I get two solutions from the sine, the cosine part. It's the same idea here. When I get one, I get the other one for free because they always come in this conjugate pair. Let's see an example of what this might look like. I want to find the eigenvalues corresponding eigenvectors for the matrix 1, minus 4, 2, minus 3. So let's start as we always do by finding the characteristic equation and looking for the roots of that equation. So a minus lambda I, take the determinant. This is the determinant of 1 minus lambda minus 4, 2 minus 3 minus lambda, which is equal to minus 3 minus lambda times 1 minus lambda, and then plus 8 minus 2 times minus 4. So this expands out to a minus 3, a minus lambda, a plus 3 lambda, and a plus lambda squared plus 8, or lambda squared plus 2 lambda plus 5. This doesn't factor, as if we're in the complex section, it probably shouldn't. The quadratic formula will tell us that lambda, if we want this to be 0, should be negative 2 plus or minus the square root of 4 minus 4 times 5 over 2. That's 4 minus 20, or negative 16. So negative 2 plus or minus 4i over 2, or negative 1 plus or minus 2i. So complex conjugate pairs as expected. Now, because we know these are complex conjugate pairs, I know I only have to find one of the eigenvectors. I get the other one for free. So let's take a look at the plus version of this eigenvalue. So we'll take lambda to be -1 plus 2i. Now to solve this out and look at the equation, a minus lambda I times b equals 0, and solve it. So a minus lambda I in this case is 1 minus -1 plus 2i, -4, 2, -3 minus -1 plus 2i. You be very careful with your signs here and how this stuff works. It's still 1 minus lambda and then -3 minus lambda, but lambda is now a complex number that has two parts to it. So let's collect some terms here. This matrix becomes 2 minus 2i, -4, 2, -2 minus 2i. And at this point, we're now looking to solve this out, and we should see redundant equations. Now, in the case of the real numbers, it's really easy to see when it's redundant, because for two equations, they're redundant if they are multiples of each other. But in this case, we're not just dealing with real numbers. So these equations are going to be complex multiples of each other, not real multiples of each other. And so to see what's going on here, at this point, hard to see redundancy, we're going to use complex conjugates. So I'm going to multiply this first row by 2 plus 2i, which is the complex conjugate of this number here. I want to get this first row to be entirely real numbers so I can compare them more effectively. And when I do that, I'll then be able to see what the eigenvector should look like when I have these equations simplified. So we're going to multiply this first row by 2 plus 2i. And if I do that, I will get 2 minus 2i times 2 plus 2i, -4, 2 plus 2i, 2, -2 minus 2i. I'm going to now expand out and simplify some terms. This is a 4 minus 4i plus 4i plus 4, so it's an 8 in that first spot. I get -8 minus 8i to -2 minus 2i. And now it's easy to see these equations are redundant. They're the same equation, just one's now a multiple of the other. And because I put one column entirely real, they are now just real multiples of each other. So I can reduce this. I can divide the first row by 8, the second by 2, and then use them to cancel. And I will get to the system that looks like 1, -1 minus I, 0, 0, times v1, v2 equals 0. Which tells me that v1 plus -1 minus I, v2 equals 0, or moving that to the other side, v1 equals 1 plus I times v2. I want to pick a non-zero vector to solve this, so I'm going to pick v2 to be 1 to make my life easier. Instead of picking v1 to be 1, let's pick v2 to be 1 to make our lives easier. So if I pick v2 to be 1, I get that v1 should be 1 plus I, and therefore I get my eigenvector to be 1 plus I and 1, for lambda being -1 plus 2i. Then from this we get as a bonus that the vector will be 1 minus I for -1 minus 2i, because the conjugate always has the conjugate eigenvector. And if you were to work this out independently on its own, you would get this eigenvector as well, or at least a complex multiple of it for your eigenvector. So that's the idea of complex eigenvalues. The fact that they show up is sort of a necessary consequence, and how you can work out what they are. The key point that's going to be an issue here is the redundancy of the equations. And the easy way to figure that out is to get one column to be entirely real numbers. Then it's easier to compare the equations to each other and make sure they are redundant. Solve this out. If they're not redundant, the complex number is likely wrong in some way. You want to go back and check that. You should always get redundancy, and if you get one column to be real, you'll be able to check it and then find these complex eigenvectors for the corresponding complex eigenvalues.